Welcome to the last episode of Garden Mechanics. It's a sad day, it's the season finale, but it had to end somewhere. Today we're going to be looking at some more incline plane problems. I'm going to be setting you quite a tough challenge, which I want you to have a go at and spend some time on. And then we're going to look at some more complicated incline plane problems and some incline planes with connected particles. So the work today is going to be from book 2, and I will put the exercise references in here. But let's get to the challenge question and get started. So here I have 2 meter sticks. This one goes up a meter and this one goes along the floor a meter. Okay. Now, today's challenge question is all to do with ramps. And the challenge is, how can I get something from this point here at the top to this point on the ground in the quickest way possible by only using gravity? So we can't push it or accelerate it somehow, we can just let it go. What's the quickest, or what sort of ramp or track is going to take it from here to here the quickest?
Ooh.
That's broken. That's broken so many times. It always comes back. It's like the phoenix. So the 45-degree slope will be the most basic option, but it's up to you. So you could think about maybe having 2 slopes, a curve, a slope. You may want to come above this line, then down. But it's up to you. But it's quite an open-ended challenge, and I want you to think about all the work we've done on slope and on incline planes, and see if you can get to some sort of conclusion about it.
Ready? Nailed it.
So as we can see, the time for a 45-degree slope is about 0.65 seconds. Here I've labelled up the diagram for the simplest option, which is to have a 45-degree slope. We know the acceleration is going to be g sine 45. If we have 1 meter up, 1 meter across, that means our slope length is root 2, or 1.414 meters. To work this out, I've drawn the suiva up here as well. You're going to have to use a rearrangement of s equals ut plus a half at squared. And when I've done this, I've got to a value of 0.638 seconds, which is quite satisfyingly close to what we've got. So you're going to use this formula. And what you can do is you can start off maybe with 2 parts to your slope. If you want to go further, you can then add some more. GeoGebra is really good for modelling this, so if you want to use that, that's also a good idea. It is quite a tough challenge. I am going to leave it up to you for the moment, but I will post a video with my ideas on it. But yeah, see what happens. Is the 45-degree slope the quickest, or is it going to be something else? And here's a little video to give you a clue as to what might be the best solution. But whatever you do, I just want you to see what happens and justify it with the mechanics that we know so far. It's quite a rabbit hole to go down, as I've found out, so be a bit careful, but just have a go, simplify it, and then once you're confident, complicate your model and see where you get. So the second part of our inclined plane work is looking at 3 different examples of when we'd use inclined planes. The first one is a plane with multiple forces acting on a particle. The second one is when we have connected particles over a pulley. And the third one is when we have a static situation. Each one's a slightly different bit of working, and we're going to go through 3 examples to help you work them out. Okay, so here we have a particle, and the first example we're going to do is a frictionless plane of 30 degrees inclination. We have our particle here. I'm just going to hold it here for a second, and I'm going to label on some forces, and we're going to combine them and resolve the forces on this particle. So I'm going to put the forces on now, and what I want to calculate is the acceleration of the particle up the plane. Okay, the first thing I'm going to do is I'm going to label on some more forces that we've got. So one of the forces we have is a reaction normal force here. We also have the weight of the particle straight down. we have the component of that force which is perpendicular to the slope, and we have the component of that force which is parallel to the slope. Okay, so we know that this angle here is 30 degrees because this angle here is 30 degrees. This one is 3g. This component is 3g sine 30. This component is 3g cos 30. Okay, here's our reaction normal. Now we're not really going to use the forces perpendicular to the slope, but it's important to label them on anyway. The last force to look at, or the last bit of detail to add, sorry, is this 15 Newton force here. Now if I draw a line which is parallel to the slope, hopefully you'll see that because this 15 Newtons is parallel to the base, then this angle here must be 30 degrees as well because of Z angles. So we have a big Z here, and this, because it's horizontal, must be at 30 degrees to the surface of the slope. Now what we're going to do is we're going to consider this whole thing, and we're only going to consider the forces parallel and perpendicular to the slope. So just to help you get your head around this a little bit, I'm just going to rotate this whole diagram so that the slope is horizontal. I'll show you what I mean. So if I rotate this round, now the slope is horizontal. The forces we're going to be dealing with are just the forces that go left and right and up and down. Okay, and so the next thing we're going to do is redraw this as a point diagram and work out what all these individual forces are. Okay, so we have our forces labelled on. We have our sort of gravitational forces that we're used to here. We have our 3G and our two components of the weight. I have my reaction normal force here. I have my 15 Newton force at 30 degrees, so that gives me a component into the plane of 15 sine 30. I then have my 15 cos 30 up the plane. I have my 10 Newton force up the plane at no angle. And finally, I have my 5 Newton force at 10 degrees from the plane. So I have a component of 5 sine 10 and 5 cos 10. So what we need to do now is we need to draw these on a point diagram. And we're only going to consider the forces up the plane, down the plane, and into the plane perpendicular. So let's sort those out first. So there's one force, sorry, there's one direction here, and we want to work this out. So what forces are going in this direction here? Well, we have our reaction normal, plus I have 5 sine 10 is going in that direction. I also have 2 going the other direction, so it's just those two for the moment. So 2 going into the plane, okay, well we have 15 sine 30 over here. So that's going into the plane. Plus I have 3g cos 30. Okay, so I can almost just tick them off. So I've done that one, that one's done, that one's ticked off, and that one's ticked off. Okay, great. So we've got all the forces perpendicular to the plane. Right, now let's look at the forces parallel to the plane. Let's go down the plane first. So the forces down the plane, well, it's actually just this one. 3g sine 30. Okay, the forces going up the plane, well, I have my 10 newtons, plus I have 5 cos 10 going this way. And I also have my 15 cos 30. So the question is, what's the acceleration up the plane? So for this question, I actually don't need this force or this force. So for the moment, I don't need those two. When we bring friction into it, I will need those. But for the moment, I just want the forces up and down the plane. So what I'm going to do is I'm actually going to get rid of this diagram here. And and we can just work from our force diagram. Now we know it's going to go up the plane, so what I can do is I can start with F equals ma. Now my resultant force is going to be this force here subtract this force here. So my resultant force is going to be 10 plus 5 cos 10 plus 15 cos 30 subtract the gravitational component down the plane, which is 3g sine 30. Okay, and all of this is going to then equal ma. Okay, well we can just put this into a calculator, but there's no unknowns here, so we can work out what this force is. I'm going to do that now. And I get a value of my resultant force of 13.214 ... I'm going to keep this number accurate, newtons. Okay, so I have 13.214, and that equals 3, the mass of my particle, times by the acceleration. So my acceleration is going to be my resultant force divided by 3. So this gives me an acceleration of 4.4 ms to the minus 2. Okay, so what I did is I took this force here, which is my 3 combined forces up the plane. I took away my force down the plane. I used F equals ma, and then I divided by my mass as a final step to find the acceleration. Okay, with that point method in mind, have a go at some of the questions on task 1. Okay, for our second example, we're going to stay with a 30-degree plane. We have a 3 kilogram particle attached via inextensible cable to a, let's go for a 10 kilogram particle to make sure that it moves. We're going to have a frictionless plane. So we need to draw it out, label it up, and work out 2 things. I want to know the acceleration of the whole system, and I want to know the tension in this cable. The second version of this question is do exactly the same, but we're going to have a coefficient of friction instead of it being frictionless. So we're going to have a coefficient of friction of 1/4, 0.25. So there's 2 questions to work out. Let's see what happens. Okay, so I've redrawn the diagram here, and so I'm just going to start labeling on the forces we need. So we have a 3 kilogram mass here. This particle is 10 kilograms. We're going to have a tension going upwards towards the pulley on both sides. We have a 10g weight downwards. On this side we have a 10g weight downwards from the 3g, and we will get the component forces for that. So this is 30 degrees. So we have 3g sine 30 and 3g cos 30. I'm also going to label on my reaction normal because we will need it when we bring in friction. So for the first question, we need to draw 2 equations. So the first equation is going to be 10g minus t equals 10a. My second one is going to be, this is for the 3 kilogram particle, is t minus 3g sine 30, and that equals 3a. If I add these together, I knock out the t's, and I have 10g minus 3g sine 30, and that equals 13a. Okay, so I can just put the left-hand side here into my calculator, divide by 13, and I will get to my acceleration, which comes out to 6.41. Let's try minus 2. So we can then find the tension by using our first equation. So our first equation, I'm going to write T equals 10g minus 10a. So in this case, it's going to be 98 subtract 64.1, and that gives me a tension 33.9 newtons. Okay, so there's my answers for a frictionless situation. Now, if we bring in friction, we said we have a mu value of 0.25. So I'm going to have to add in a component of friction here, Fr. Now this Fr is going to be mu times by my reaction normal. So my Fr will be 0.25 multiplied by 3g cos 30. So all I'm going to do is I'm going to write my two equations again and incorporate this force into it. So we have 10g minus t equals 10a. That one stays exactly the same. I then have, for my 3 kilogram particle, t minus (3g sine 30) and also minus 0.25 times 3g cos 30, because this is my frictional component, and that equals 3a. So again, if I combine these together, add the two equations, I will end up with 10g minus 3g sine 30 minus 0.25 times by 3g cos 30. And this equals, again, 13a. So again, it's just a case of putting it into your calculator, finding the left-hand side, and then dividing by 13. If I do this, I get a value of 1.97 for my acceleration. And then if I do the same and put it in for my tension, this gives me a tension of 78.3 newtons. Okay, so by having this frictional force, what happens is it stops this 3 kilogram particle from moving up the slope as easily. Therefore, we get a lower acceleration but a higher tension. When we don't have friction, we have a higher acceleration and a lower tension. Okay, so with a connected particle, you need to do your two equations again, but be extra careful with the one on the slope. Okay, make sure you've got all the forces labelled on. Okay, so have a go at some connected particles questions with inclined planes. Okay, my third and final example is we're going to change this slope slightly. So we're going to have a 45-degree slope. Okay, and I'm going to have a 3 kilogram mass. I'm going to apply a force to hold it in place. So this force is horizontal, just to hold it in place. The coefficient of friction, okay, is still 0.25 or a quarter, but I want to find what force I have to apply in this direction in order for this to stay in equilibrium, to stay at rest. So inclination of 45, 0.25 is mu. I'm applying a force here, and I want you to find what this force is if the particle's about to go down the slope. Okay, so it's about to go down the slope. I'm just holding it so it doesn't slip. Okay, let's work that one out. Okay, so for this question, we have a force of x newtons, which is holding this particle in place. We have a horizontal force, and it is stopping this particle of 3 kilograms going down the slope. So we're told it's at the point of slipping down. So the first thing we can think about is if it's at the point of slipping down, it means that our frictional force must be acting up the slope. Okay, so I'm going to label that on straight away. If it was about to go up the slope, it would be acting down, but because it's about to go down the slope, it must be acting in the opposite direction. So then what we can do is we can add on the forces we always need to add on for an inclined plane. We have the weight of the particle, 3g. We have our two component forces, 3g cos 45 and 3g sine 45. We also need to put on our reaction normal force into the plane. And the final thing you need to do here is split up this X force, because if you think about it, this force here is not perpendicular or parallel to the plane. So we need to split it up so that it is. So I'm going to draw a component force down into the plane, which is perpendicular to the plane, and one which is parallel to the plane, this way. This angle here is 45 degrees. That's because of Z angles. Okay, this X force and the base are parallel, so this must be 45 degrees. Therefore, this component here is X sine 45, and this component here is X cos 45. Okay, so I've got a fully labelled up diagram, and I've got 1, 2, 3, 4, 5, 6 forces which are either perpendicular or parallel to the plane. Okay, so this force now, this X Newton force, I don't need to worry about because I've got its components, and this 3G force I don't need to worry about because I've got its components. So if I move over here to this point diagram, I'm going to label on the forces and their directions on here. So up the slope I have FR, and I've also got X cos 45. Okay, down the slope, I've got 3G sine 45, and that's all the forces up and down the slope. I've got this one, and this one. Okay, so now perpendicular, going upwards, I have Rn, and going into the plane, I have 3G cos 45 plus this force here, which is the one that's often forgotten about. This is the force into the plane from X, so X sine 45. Okay, so let's do a quick count up. We had 1, 2, 3, 4, 5, 6 forces. On my diagram, I've got 1, 2, 3, 4, 5, 6. Perfect. So what I need to think about now is, well, this is a static problem, so these forces must be equal. So what I'm going to do is I'm just going to draw two equations. I'm going to equate Rn and this part. So I'll draw that down here. So Rn equals 3G cos 45 plus X sine 45. Essentially what I'm saying is the weight into the plane plus this extra component from this X force for creating this reaction normal. And then I'm going to equate 3G sine 45 and FR plus X cos 45. Okay, so what's important to realise here is that it's like a simultaneous equation, and I'm going to substitute this one into this one. But I'm going to substitute it using this FR. So it's also worth me defining what FR is. Well, FR is mu Rn, and our mu value was 0.25 or a quarter. So my FR must therefore be 0.25 multiplied by 3G cos 45 plus X sine 45. Okay, because it's my coefficient of friction times my normal reaction force. Okay, so going back to the second equation, I'm going to write this out. So I'm going to write 3G sine 45 equals 0.25 times 3G cos 45 plus X sine 45 plus X cos 45. Okay, so there's a lot going on in this equation, but the thing that's really important to notice, I'm just going to choose a different colour for this, is that I have an X term here and I have an X term here. Remember that we want to find X, and so we're going to have to at some point factorise X out, okay, in order to find its value. There are no other unknowns. We've got g, we've got cos 45, sine 45, but there's no other unknowns. So what I'm going to do is I'm just going to expand this out and then rewrite it with my x's on one side, my x terms on one side, and my non-x terms on the other side. Okay, so I've drawn this out with my x terms on the right-hand side. Now what I'm going to do is I'm going to factorise out x from this side. Okay, so this side is going to become x 0.25 sine 45 plus cos 45. Okay, this side remains the same, so I'm going to be a bit cheeky and just copy and paste it. Okay, so now if I divide by this bracket here, I end up with x equals 3g sine 45 minus 0.25 3g cos 45, and this is all divided by 0.25 sine 45 plus cos 45. Okay, now I'll put a little note here. Well, I won't put it there. Be careful. Be really, really, really careful, because when you put this into a calculator, you need to make sure you've got your brackets in the right place. Now, brackets, just out of habit, put them around the 45s, here and here. Okay, when you put it into your calculator, be really, really careful. Okay, if you put it all in correctly, you should find you get an answer of 17.64 newtons. Okay, so it's quite a lot of work and it's a big old question, but when you have a static problem like this, you must draw a diagram, a point diagram, set things equal to each other, and then work it through. In here, just make sure you don't drop any g's, don't drop any coefficients of friction, and make sure your negatives are correct. Okay, yeah. If you can do this question, you'll be able to do the rest of the questions in task 3. Have a go. So good luck with this week's work. If you've got time, work back through other things that you found difficult. Have a go at the work in the textbook, and I will see you back in September.